So I'm a PhD student here at Queen Mary's, and my research involves trying to model people's experiences while they play AR games. So in this particular study, I'm going to talk to you about some initial testings that we've done in terms of trying to computationally model players' preferences within AR games. So a little bit about what I mean by modeling player preferences. Like I said, it's using computational models to be able to predict what people like around different types of game content within these environments. So first, let's just take a brief look at consumer AR mobile games right now. So on one hand, you have games by Niantic like Pokemon Go and Harry Potter Wizards Unite, which are more location-based AR games. These sort of games make people travel to different areas and try to promote healthy behavior through different types of game rewards and narrative. And on the other hand, you have more local AR games. By this, there's an example of Dark, which is a horror-based AR game, which sort of does not involve people traveling to different areas, really. You can engage with the game within your local space. And we see this trend of these sort of games coming up, potentially because mobile companies like Google and Apple have started releasing AR SDKs to be able to conveniently build and develop these type of games. So moving to the research side of things, there seems to be a whole lot of interesting examples going on in terms of research applications of AR. So on one hand, the image on the right, what you see is an example of procedural content generation for a game of Lemmings. For those of you who don't know, Lemmings is a game where you guide a herd of creatures from a beginning point to an ending point. This game is predominantly played in like a 2D desktop type of environment. This is an example of it being done in AR on the fly. The idea is different types of AR environments would require different types of procedural content generation to be able to map the game onto the environment. And another example is a multiplayer AR game, which is more puzzle-based, where people can collaborate, and there's a social element to it, where people solve this grid-like puzzle by picking up blocks that are distributed around the room and being able to arrange it within this grid. So the main takeaway from this is there seems to be a lot of interesting prototypes going on. Designers are really looking at the potential and different things that are possible with these sort of games. However, we did notice a gap, really, where there doesn't seem to be a lot of studies that investigate player preferences within these games or player experiences within these games, and that's where this study comes in, really. So in these sort of AR mobile games, people go through a local space, and a lot of their interactions involve embodied interactions, meaning they use their body to a high degree to be able to accomplish different objectives within these games. So what we did was we decided to collect player movement data and extract these movement-based player behavior features and try using these features to model emotional preferences of these players. The idea is movement stays common between these games, so if you had a generalized way of extracting information from this movement and using it to predict player preferences, this would be useful for a number of applications of these sort of AR mobile games. So in this study, what we did was we developed an AR treasure hunt game. We conducted a user study with this game in order to collect player behavior data and their corresponding preferences around different versions of this game. And we proceeded to perform some amount of statistical analysis and preference learning methodologies to be able to predict these preferences. So I'm first going to run you through the AR treasure hunt game that we developed. So these are the screens that the user would see as they progress through the game. So first, the user would get options to be able to place the game environment within their local space. They would then start off their gameplay, and they would explore this environment. By default, they don't really see treasure. They're encouraged to explore this place completely. They're given some amount of audio-visual clues. When they're near a treasure piece, bubbles start appearing, so they're indicated to go towards that direction. And when they're close enough to treasure, treasure appears. So figure 4 shows you what the treasure looks like, and players collect it by moving their phone into the treasure and collecting the treasure. So according to the story of the game, these treasure pieces are actually pieces of a picture that have been broken up and distributed into your world. And you collect this treasure, and then once you exit the space, you're presented with a 2D puzzle that you then put together to be able to appreciate the picture. A player that does not explore the place space comprehensively does not see the full picture at the end of it. And in this case, in between figures 5 and 6, the player did not collect 3 treasure pieces, so they are not as rewarded as a person who would see the entire picture at the end of it. Also, figure 4 is sort of been placed for your understanding. Like, generally, these treasure pieces do not appear so close together. They're like randomly distributed across the space, so it's actually challenging for them to explore the space and be able to collect these different types of treasure pieces throughout the space. So what you're looking at is pictures from the user study. So the game was designed to be played in open spaces and parks. This decision was mainly taken because the technology right now, and if you're developing for AR, would know the difficulty around preserving this mapping in indoor spaces where lighting conditions is not good, and also indoor spaces tend to be noiseless textures, meaning predominantly colored textures, and this technology doesn't seem to work as well. So outdoors works great because it's a really noisy environment. Things like mapping and tracking seem to be a lot more stable in these sort of environments, and also daytime. So a little bit more about the game itself. So the game was developed in such a way that each level is sort of generated using 2 parameters. Right now, we've kept things quite simple, where each parameter has like a high state and a low state. And the 2 parameters that we chose for the game itself were number 1, area of the level, and number 2, the number of treasure pieces within this level. So the image itself sort of shows you an abstract representation of what I mean. The blue boundaries represent the boundaries of the AR level to sort of constrain the user so that they don't go wandering to unsafe areas and things like that. And the red dots are the treasure itself. So that's just to give you an example of how treasure could be distributed through the environment. Every time you load the game, it's in different spaces, so it's not really predictable. And also, people do not see these treasure pieces. The green box represents an exit area where the players asked to go into the exit area once they believe they've gotten all the treasure pieces. They aren't told how much treasure there is distributed in the space in advance to keep a certain amount of curiosity and mystery to the experience itself. Moving on to information around the user study itself. So we recruited an opportunity sample of people around the university itself. We had 42 participants take part in this study, 17 of which were female, 25 were male. Their ages ranged from about 18 to 44. However, more than half of them were between 18 and 24 because they were predominantly university students. And we did collect some amount of information regarding their previous experiences playing AR games. 45% never engaged with these sort of games before, while the remaining have tried out a few of these experiences on their phone, and about 5% of players were heavy AR game users and predominantly Pokemon Go. So a bit about the user study itself. People were first briefed, and then they took part in 3 sessions of the study. So they played 2 versions of the game, where each version was very different with each of these parameters. And at the end of it, they answered something called a 4AFC questionnaire, which sort of collects their preferences between the game, and then they were debriefed. So along the game, what we did was we collected a bunch of data. Number 1 was their preference data through the questionnaire, which I'll tell you about. Their movement data during the game, which was sampled at about 64 hertz, and their score as they progressed through the game. So in this study, we focused on 5 dimensions of emotions that we were interested in, which has been highlighted in previous literature as emotions of interest while playing video games, not necessarily AR games. And the question below gives you an example of the 4AFC protocol for fun. So they are asked which game was more fun. Was it the first game or the second game? Were they equally fun, or were neither of them fun? And we proceeded to do this for each of those dimensions. So we collected all this player behavior data and their corresponding emotional preferences, and there was some amount of data analysis that was performed to the movement data. So the data was first pre-processed, where filters were run through to remove noise from the data, and then a certain amount of player movement features were extracted from this data. So the study contains about 63 features, which I'm not going to go into right now, but we coupled them with 2 controllable game features, which was area and treasure, and used these 65 features in statistical analysis and preference learning. The statistical analysis involved correlation analysis to look at which of these features correlate with which of the emotional preferences that were expressed by players. And the preference learning techniques were more about modeling these preferences to be able to predict them. So again, what we did was we combined 2 games by extracting their features and taking the difference from these features, and that was the input for a model of classification which we tried out. So ground truth came in from the 4AFC protocol, and we investigated two methods of classification. One's a binary approach, where the model tries to tell you was the first game more fun or was the second game more fun, for example. And the other was a ternary approach, where the model also did try to tell you whether there was no preference expressed between these games. So we did have to apply some amount of feature selection to be able to increase the performance of these models. And finally, these are the results that we got out of it. So number one, out of the classifiers that we tested for this data, the SVM classifiers seem to perform the best. All emotions seem to perform better than random chance. The classifiers seem to perform better than random chance. However, specifically challenge and frustration seem to be the easiest to predict in this particular context. So the graphic that you're looking at are the tenfold cross-validation accuracies from each of the emotions tested. The blue bars indicate the ternary classification accuracies, and the red bars indicate the binary classification accuracies. And so binary does perform way better, but it is trying to model a much simpler problem in this case. And challenge and frustration perform in the binary case well above 90%, and also they're quite stable, meaning the error bars are not as wide as compared to the other emotions that we tried to model using this methodology. So in terms of where we go from here, so right now we have a proof of concept methodology in a very simple game-based environment. What we'd like to do is try out this methodology in a more complicated AR game, which is parameterized in a more complicated way. Let me put it to you that way. Number one. Number two, we'd like to further investigate to what extent these player movement features can be used to understand players' balance and arousal, because to certain extents, challenge and frustration could be misinterpreted by players. There seems to be a high degree of overlap between people's understanding of these two emotions. So we thought we would take a balance arousal approach to truly distinguish between good experiences and bad experiences, and high arousing experiences and not so arousing experiences. And finally, we thought the final goal of this work is to be able to use these player models to dynamically adjust games on the fly. For example, in physical AR games, or games that require you to exert physical effort into the game to be rewarded from it, different people have a different degree of physicality with which they can play the game. So it would be interesting to look at how we can use these models to tune difficulty of these sort of exercise-based games to benefit players themselves. Yes. Thank you.
Thank you. Here's time for a couple of quick questions.
I just want a bit of clarification. You said you're going to be using basically motion to. What do you mean exactly about motion? It's rotation, inflation, accelerometer data, gyroscopic data. So what can you describe it more?
Sure. So right now, what the AR SDKs do for you is they perform some amount of sensor fusion and can return the position and rotation of the device in space. Now what we do is we record this position and rotation. However, we don't work with exact position and rotation values. What we do is we investigate the rate of change of these things, looking at it in terms of velocity, acceleration, and the derivative of acceleration, which is jitter itself. So we look at the rate of change of these things to try modeling how people feel while playing these games.
Yeah. So just on this slide, actually, so you were saying that you feel that people might misunderstand the idea of frustration, and I feel that if you're going with balance and arousal, people will have a harder time understanding these concepts.
I understand.
Personal experience.
So this is something that I've been thinking about for future studies as well, and that it wouldn't be possible to take a preference learning approach to do this. So in this case, it wouldn't really be asking people in this sort of format of comparing two experiences. There are a number of methodologies from literature itself that lets you record preference and arousal through questionnaire-based approaches, but it would be on a single game basis, if that makes sense.
But you just change from a preference-based things to a rating, right?
Yes. It would shift the way of modeling this, definitely.
Yeah, so that would introduce new biases into your...
Yes.
Also, I disagree. You can use preference with balance and arousal?
So it would have, you could use it to model it through a preference learning approach. It would sort of be using some of the techniques that you talked about in your study, where you look at the difference of preference and arousal and use that in a preference learning model. These are things that I can only speculate on because it's very much work in progress that we're working towards. Ideally, there seem to be these two approaches which both would be investigated, but ideally we would take a preference learning approach just to be able to control for subjectivity in terms of answering and things like that. Yes.
Any other questions?
Just one comment. At some point you mentioned that you had decided to not announce, in your particular game, not announce how many pieces of treasure were there. That's a choice, but I guess it has a lot of influence in the, for example, in the frustration of the players.
Yeah. Yes. Exactly. Yeah.
You don't know when you are when you have had enough, you stop, but then you're frustrated because you miss some essential.
Yes.
So is that? Can you do better?
Yes, so right now what we wanted to do was create an exploratory experience that in the game itself, like as opposed to a physical-based game where the person exerts effort into the game using their body, we wanted to keep it open-ended and exploratory by nature. And the choice of telling players not telling the players the number of treasure pieces within the game was sort of just a design decision taken to keep people focused on exploration as opposed to task completion, if that makes sense. So going forward, and yes, there is definitely some amount of bias introduced in terms of what can be predicted depending on the game tasks, because you are using your body to do these tasks, which is why we thought of changing the dynamics of the next game that we use, where yes, the game does bias your body in a sense and bias your interactions within the space. And so again, in theory, because we're looking at the rate of change of things, it should work, the similar methodologies, but I cannot comment on that right now.
Yeah, very good. Let's thank Vivek once more. In our next talk, our next talk by Emanuele Salvucci is ToonToy,
which is
a node-based NPR solution for Unreal Engine
this one.
Yeah, you can use that.
4. This is the graphics paper of the session.
Hopefully, yeah. Just.
I missed the signature of the previous speaker. Okay.
Right, hello, good afternoon. I'm Emanuele. I'm Technical Art Director of Revolution Software, which are probably best known for having developed some classic adventure games like Broken Sword, Beneath the Steel Sky, early on as well, Lure of the Temptress, so they're around since 1989, probably. Today I'm presenting the game that's been, the work that's been done for the next title, which is Beyond the Steel Sky, which is a sequel to the classic Beneath the Steel Sky, which is a non-photorealistic rendering solution for a real engine. So, of course, since the game was supposed to be non-realistic, a real engine is well known to be hyper-realistic engine, so all the technology and the focus of the technology goes into creating hyper-realistic graphics in real time. Of course, we needed something that was utterly different. There was a lack of integrated NPR solutions, so commercial engines only tackle what's commercial, and realistic rendering is currently commercial, and it will be, because a nice PhD, a master thesis by Nathan Jarvis says there isn't a lack of interest from the players in playing stylized games. There's rather technological bias well, from from companies producing technology to make games. So it's nothing to do with the taste of players. It's got to do with what technology is available and what the technology provides to the developers. And then again, the other motivation is that we had Dave Gibbons, which is a co-author of The Watchmen, the original comic book, as starring again in the project. It was making the first ones. It was making Beneath the Sea Sky, and it was again into the sequel. So that's even more pushing the boundaries. So we started working on our own solution, which is a node-based post-process shader. It's fundamentally based on a standard digital 2D drawing pipeline, so where the artist typically proceeds in three stages, which is inking, coloring, and compositing. In our case, the inking stage comprises 5-line rendering algorithms. Some are well known, like the Canny algorithm, XDOG, and some other are proprietary at the moment. We also support most of the engine post-processing effort that come, integrated, like bloom, depth of field, and motion blur. And we are HDR compliant, which is in NPR rendering. It's like, okay, you're supposed to go 2D, so what about HDR? It poses a number of problems when you draw lines, when you deal with color that are new to the field. So yeah, I was told by one of the reviewers of the paper, you've shown the graphics, that graph that you show is very little. So I admit I have difficulties working with that in a reel as well, even though I can zoom in and out, because it's probably composed by more than 600 nodes, and some of that nodes are subgraphs or sub-functions containing even more nodes. So it's difficult not just to display in a slide; it's difficult to work with it. So this is how it looks. This is how you create stuff like that in a real engine. So of course, this is not what gets processed by the engine. All of this is compiled on the fly into actual HLSL shaders by the engine. But ideally, you're supposed to visualize that as each pixel of the image entering on the left side of the graph and finishing as an output to the right side of the graph. Do that for all the pixels on the screen, so you get the idea of what's happening under the hood. So yeah, during development, the number of features and algorithms implemented, it grew steadily in time. Today, ToonToy comprises more than 500 independent parameters and supports stencil-based settings for specific categories of scene objects such as characters, sky, fluid, and foliage. All of this because we didn't just tackle the problem of creating a single style. We wanted to experiment with visual style at the very early stage of the project. So we wanted to try many things, and we never discarded any feature that we implemented, so we kept them all so that we can play with visual styles. Now we're able to create a large variety of visual styles as a post-process effort. So, of course, given the number of algorithms that we used and created for ToonToy, we would like to focus on one implementation of those, which is the Canny edge detector. So if you're not familiar with that, Sobel and Canny operators, I would recommend watching Dr. Michael Spawn's video on YouTube for a quick introduction, which is actually very good. Of course, unfortunately, both these videos take 15 minutes, so for me, it's possible to cover the same matters in that time. And of course, possibly I couldn't explain it better than it does, so it's recommended. So the Canny edge detector algorithm is an algorithm that's been published in 1986, and it's applied to the output of the Sobel algorithm. It's a multi-pass, or rather multi-stage algorithm, because we make a distinction between rendering passes and different stages of the algorithm itself. What it does is it finds, of course, by the name, it finds edges into an image. of course, the image is supposed to be 2D. So in 3D, we're working with rendering buffers, which are still 2D images, but generated on the fly by the engine through the geometry and all that. So the very nice properties we look after in the Canny operator is that it generates 1 pixel wide lines, and it's resolution independent. Those features are also artistically interesting, not just in the field of computer vision, object recognition, because Canny algorithm is mostly used in that field as well. So in literature, we surprisingly found a few implementations of the Canny operator as GPU shaders. So it's quite old algorithm, but most of the research is apparently focused on FPGA and GPU implementations rather than pure shaders. The few shader-based implementation that we studied used multiple render passes on the renderer. So there was a Gaussian blur pass to filter out the noise. There was a second pass to generate the age gradients, and a final pass to perform non-maximum suppression and thresholding. So in our case, the input can be considered noise-free because the input traditionally in a Canny operator is a natural image, is a photograph. So they have to eliminate noise and then proceed with the next steps. So we're generating the visuals, so it's supposed to be noise-free. We can skip the Gaussian blur pass. Of course, we then implemented the algorithm as 2 render passes in the engine and as a single render pass in the engine, and wanted to compare performance and see how it performed. So really briefly, in our single pass implementation, we generated the first age gradient and determined the UV offset for the forward and backward samples. So the depicted nodes basically are material functions, as we mentioned earlier, that contain even more nodes. Then we generate the edge gradient again twice for the 2 samples and perform line thinning and eventually thresholding. And that's the result. Of course, the timing, we took the timing in GPU as GPU processing time is 0.43 milliseconds for a multipass and 0.42 for a single pass. So on average graphic cards, I mean, it's basically the same. I mean, whatever you do, it's a single pass is got more advantages into the engine because you can use its own post-process effects as well. Multipass poses a number of problems, so single pass is preferred solution at the moment. So we, at some point in early stages, we wanted to demonstrate that all of this work for the game, that we want to get from this result from the engine to something like that without touching the graphic assets. So we wanted to do everything automatically. To do that, we didn't have any asset in the game, so we wanted to test actual, content, production content. So we took Infinity Blade graphics released by Epic Games and applied some styles, and see how it looks. And we wanted to see if we were able to do that without doing anything specific to the graphic assets, and see if our technology worked anyway, or if we had any issues of any kind. So these are the styles, the tests we made initially. But of course, that was 1 year ago. When Epic Games released Paragon assets, we took the opportunity to extend this test and see if we could create like a short movie that looked like an animated movie out of their game assets. So we created Paragon Tribute Tech Demo, which is entirely made out of Paragon assets without modifying the original content, if not probably maybe 2 materials that got in the way of the final look. This is, of course, it's not running in full. It's an HD. Its running time is about 2 minutes and a half. It wants to demonstrate also that you might be able to do animated series straight into the game engine rather than go back to CGI, go back to production. If you want to do an animated series out of your game content, like to name one, Halo, it's running animated series on Netflix, so you might want to use the game content straight into the development environment where you're working with and just create the animated series. That one might be an option. So to sum it up, it's Right, it took less than a week to make the sequence editing. We made sequence editing both in the engine and with standard video software, and we found out we made that 3 times faster in the engine. All post-process efforts were created in Unreal Engine, and we did just minor changes to material. Of course, the main purpose of the technology was to serve as the styling renderer for Beyond the Steel Sky. That's the latest we can show of the game. I think we actually reached the goal. Internal people, the art director, were really satisfied with the results, so we actually used the technology for the game. The biggest challenge we had with this one was that when it was accepted as a mobile exclusive for the Apple Arcade service, we had to deal with mobile, which is an entirely different story. I mean, we went from shader mode 5 high-end platforms like a PC to mobile devices up to very low-end phones, very different screen resolution. Of course, the engine that helped a lot, but we had, as a basis, we had lots of post-processing going on, lots of algorithms that needed to be adjusted and all that. So performance was a concern as well. Fortunately, we overcame all of this, and hopefully the game will be released end of the year. So, thank you.
Impressive graphics. Questions? I was wondering. So, in a multi-pass approach, you are not able to directly handle transparencies, and even in this image, I guess the glasses. Well, there are no transparencies in everything you showed, if I recall.
Yeah, we got that. The glasses are.
I wonder how you are handling that.
Yeah, that's interesting because translucency apparently is also a problem for Unreal Engine itself. I mean, they struggle to deal with that as well. They propose multiple solutions inside the engine, multiple settings and all that. They, as a key factor, they provide a point into the rendering pipeline where you can put your own shader. So you want to put it after translucency, separate translucency. So you have a channel on your own dedicated to translucency that you have access from the post-processing shader. So you have the translucency buffer as a separate one. So I can deal with it directly. So I can get all the color that's being rendered into translucency pass. I can dim out the line rendering on the translucent objects. I can do all sorts of things. The problem with that is it doesn't work very well together with their own post-processing efforts, such as depth of field, motion blur. But they will eventually get there. So it's not just ToonToy that. It's a hard time dealing with it. It's a real engine as well that needs to improve in that side. Thank you.
I was just wondering if you have any data in terms, because post-processing can be rather heavy. If you have any real data in terms of how much time does it take to have a post-processing just for something like this?
You mean time as a performance of the...
Yeah.
All right. Okay. It really depends. I mean, we have a vast variety of devices that are supported. We run, of course, most tests were run on the mobile. We can't share a lot of the data at the moment because it's still Apple stuff. So might do that after the game is published. On high-end PC, well, let's say average desktop, average GPUs. Yeah. In the editor, you feel. It's difficult to work with it. I mean, you get up to, with our own average scenes, which are quite complex, you might work at 20 frames per second in the editor. Well, when it gets all compiled, it runs at least at 50 frames per second. I mean, you don't feel that, that impact on performance. There's still, of course, room for optimization, but
you don't have performance information about just post-processing shader in terms of how much time it takes.
Oh yes, in the engine we have some profiling tools that give us the timing of the shader alone. So if I can remember, it was the
Because the post-processing shader has a big advantage that it doesn't analyze mainly the data on the 3D.
Yes, yeah,
element. So
exactly, yeah.
It has no bearing on what 3D objects you have. It's just literally a pass on the image.
It's also difficult for us because it really depends on how many algorithms you activate on our own post-process. So on ToonToy, I mean, you can activate all the parameters, all of them. But let's say on our average style, we should be around 0.8 milliseconds in the GPU for the shader alone. So it's not too much. It might be improved as well. It depends on the number of algorithms you use for your style. You might use just one and improve like 10 times fold.
1 millisecond.
But almost, for what you see here, it's probably near to 1 millisecond.
Thank you.
Thank you.
Any more questions, comments? In that case, let's thank Andrei, Vivek, and Emanuele once more.
Thank you.